Daniel?
Okay. I've got Thomas, Ed, and now Mike B as well. But yeah, I think what Mike says is he likes to do global reads, where I think Thomas and Ed like to do local reads of my work. So interpret it how you will, but anyway, it's good to have Mike, especially someone who knows as much about stats as Mike does. So the talk, we've got to make sure we hit the time right. Smoothing for statistical finite elements. I've got a subtitle in there. I normally don't have subtitles, but I've gone for one this time. Mostly a primer on Bayesian filtering and smoothing, because I gave a talk to TCSG like 6 months ago, and I went and talked about FEM and our use of it inside these algorithms. And I feel like it's not that interesting to kind of go over that again. So it might be more interesting, this is kind of focused primarily actually, not for Samson, who's very well acquainted with this, but maybe more Anthony and Junhei and Zara in terms of Bayesian algorithms for filtering and smoothing, because they're really useful for data, and it's just kind of me talking out loud about them and my use of them. So to start off with, it's good to see that images are rendering nicely. We've got a problem, all right? Suppose you are in the maths department of some kind, and someone comes up to you and they ask you to find out what's going on between their data points. And they hand you this data set. So they make some observations. Those are the dots. I've drawn a loose line kind of connecting the dots. And we can kind of see, okay, there's some time element going on. So it's a system, it's a time series, right? And it's in units of radians, it's an angle of something, right? So different people are going to have different reactions to how you might answer this question, figuring out what's going on between the data points. You might try and think, okay, I know nothing about what's going on. Nonlinear function approximation. Probably going to struggle to train a reservoir computer on 20 points though. Some statisticians might say, okay, well, it's in time, but let's just regress, right? And polynomial regression, it might look nice, but you won't really know what's going on. You're just talking about a relationship between the variables, right? Some people might have the most sophisticated methods in the world, but if it's observations, those observations have noise, and maybe you're really afraid of noises, right? But let's say that we're helpful and, we want to learn more, right? So they tell us, they've got 20 measurements from a pendulum inside their lab, right? People often walk near it. The table that pendulum sits on is a bit loose. And because they don't get very much money from the ARC, the sensor is pretty bad, right? So it's not making measurements very often. It's also probably making pretty bad measurements. Complex systems, dynamical systems, a pendulum. Kind of know what those look like, right? So there's some kind of differential equation, a dynamical model, a simple pendulum with damping. Maybe I start here, right? So fortunately, it's got some parameters, right? Gravity, we know what that is. Damping, I can take a guess. I can scale things, and I can get, a curve, a time series that kind of looks like the data I started with. But you can definitely see that it's not connecting the dots very well, right? Some people might be happy with that. Let's start writing the paper. I would say no. How about we clearly have things a little bit wrong. Let's add some noise instead and see what happens, right? So why do I say add noise? Noise can mean a lot of different things to a lot of different people across maths and stats when you're sort of incorporating it into models. In this context, I want you to think of noise as representing unknown dynamics. So we were told, this pendulum sitting on a wobbly table, people walk past it. It could be the case that if things aren't assumed to be constant, the environments that surround the system by which we received a time series, that they could be impacting or throwing it off in certain ways that makes our dynamics no longer very relevant. So, all of these things alter the way the dynamics are happening. A scientist might say, let's just make a bigger model. Let's just start modeling everybody in the room and their movements, You might also say that, you just keep adding degrees of freedom, you can manage to compute it all, or you can just assume things. So, you just assume things and say, well, maybe your sensor's measurement error is so large that my dynamics are actually perfect, but your sensor's just complete garbage. Something a little bit more elegant, and maybe the disjoint categories are there for a reason. A mathematician or a statistician might say, okay, we've got a dynamical model. If we give it some structured noise, so the noise has some properties, right? Some particular characteristics to it, maybe we can use the observations to help us tell the rest of the story. So you incorporate noise, you get something that usually is written out like this. It's quite terrifying, a stochastic differential equation, but suffice it to say, we're basically just slightly perturbing the acceleration of that pendulum as we're simulating it, right? And I've got a plot here. Kind of wish the colors were a bit more vibrant, but the colors here are for the pendulum model we had before, but just different scales of noise on the acceleration as we run the pendulum. So when we've got less noise, you get some kind of behavior. You got more noise, you get something a bit more crazy going on. These are realizations from the stochastic differential equation for the pendulum. So a lot of roundabout answers here and movement. Where is this going? I mentioned they're realizations from a stochastic differential equation. Realizations are great, but what would be even better is if we knew how those realizations were distributed, and we instead looked at the dynamics and the evolution of the distribution as opposed to just the realizations. There's power in those realizations, so if you are looking at really huge complex models, sometimes any way of calculating the dynamics of the distributions is quite hard to do, and you can only do realizations. But for this kind of model, if we can work with distributions instead of explicit realizations, then we get some benefits. For starters, if you know the variance, so how the second moment of however it's distributed, you can make statements about uncertainty and you can quantify it. Likewise, if you have that distribution, you can implement Bayes' rule. So you can actually perform Bayesian inference. You can incorporate information from the system you have, whether it's observations or something else, and somehow improve the way that that distribution looks. So just to make this even clearer, what I've got up here are a whole bunch of realizations in orange from this noisy pendulum for a fixed bit of noise on the acceleration. They're the orange trajectories. You calculate just quantiles and just fill them in between, and you get these sort of clouds, these quantile intervals. And basically the stochastic differential equation, you evaluate it, and you're looking at the dynamics of those orange realizations. And what we're really interested in are evolving the clouds or the distributions, right? Because if we can evolve those, then instead we're looking at the dynamics of all possible realizations from the SDE. Okay, so how do we do that? Well, I know absolutely nothing about the beginning. There was a gap between the first observation and the start of the time series. So I just put some distribution over it. I'm going to call that X the hidden state of the model, right? Because I don't know where it is at, I just know how it's distributed. I'm going to say that hidden state, it's got a mean equal to whatever the first observation is, just a random heuristic. We don't know how the angle in radians is distributed, although I just put 2 pi on 9 there, and a variance on the acceleration of 1. We do know a little bit about the dynamics. We know that the table's a bit wobbly. And assuming nobody's deliberately pushing that pendulum, so the noise is really on that acceleration when the wind maybe pushes it, currents in the room or something like that. Let's just put noise in the dynamical model for the acceleration to 1. And so you get a state transition model that looks a bit like this. So the hidden state at the next time step is a conditional distribution on the previous state of the model at some normal, right? And then you ask, how bad are those observations? So you didn't get much money from the ARC. It's adding some noise to where it thinks the angle of the pendulum is. How bad? And they tell you it never misses by more than 0.2 or 0.02. let's just put a standard deviation or a variance of, no, standard deviation of 0.01, right? And you get this observational model that tells you how the observation is related to the hidden state. These things come together. I've assumed normality or Gaussian distributions in all three, and these constitute a Gaussian state space model. And this is basically like a fundamental construction for this kind of problem solution, right? You've got the initial density, what you think is happening at the start. You've got a dynamical model that tells you how the hidden state evolves in time. And then you've got a measurement model that tells you how observations are related to the hidden state. Why? So if you have those three things, and you also assume these two things, the first one being the Markov property of states, which basically says that if you are trying to figure out what's happening in the hidden state at the next time point, you only need to consider what's happening in the current state. You don't need to worry about what's happened in the past, just the current state will tell you everything you need to know about what's going to happen in the next step. The conditional independence of measurements basically says that the observations are not linked via some separate model that's going on behind the scenes. They're tethered to our hidden model that we're sort of working with. And these are kind of loose assumptions. Things can get more complicated if you want to go outside this boundary, but they're pretty easy to make for most models. If you do these, you make these two assumptions and you have the three things I said before, you can get a closed form solution for this. And this particular quantity is basically a conditional distribution for what the hidden state or the hidden state's distribution should be, given all the observations we've seen up until now, which is pretty useful, right? It's going to link the dynamics and whatever that sensor was saying. So you're going to somehow combine this complex dynamical statistical model with my observations and somehow get a probability distribution. Yes. And not only do you get an estimate with the mean, but you also get uncertainty bounds by looking at the variance. Yes. Are you a wizard? No, it's just Kalman sense. Worked on that one. All right. Okay, so Bayesian filtering algorithms. So, this problem of estimating what these distributions look like typically comes down to applying one of these algorithms based off of assumptions you make. So all of them are forward algorithms that try to estimate a hidden state given all the data up until that point. And just a short history, the Wiener filter is like this first archetypal example, very, very like classic. The Kalman filter is the one that, probably dominates the field, and we'll talk more about it in a second. Extended Kalman filter, I say NASA because extended Kalman filter is the thing that Apollo used for the Apollo program, or NASA used for the Apollo program. Particle filter, a lot of people like to use that because it basically makes no assumptions, and there's no single person I'm going to attribute to because it's got a lot of different names. Ensemble Kalman filter, a lot of use in weather forecasting, and then uncentered Kalman filter, something that's come out of engineering, which might be useful in my next talk, but anyway, for now. So how do they work just all together? So I mentioned that there's a closed form solution for this quantity, this distribution. The distribution of the hidden state given all the data up until now. How do you actually get that closed form solution? So we had these three things, right? We had an initial state, which in this case is basically just we have the previous state, right? The best distribution for that. We have a model that allows us to figure out this conditional distribution that tells us what the next hidden state should be. It's just the dynamical model. And we have this distribution that tells us how the observation is related to the dynamical model, the hidden state. It's the measurement model. You basically just build out Bayes' rule. So you slot it in, you do a single trick where you kind of separate out the measurement, the observation at this time point and all the history. And you can extend things out into this. And I had a few slides where I kind of did the derivations and explained how marginal probabilities and the chain rule allow you to extend them and whatnot. And I ended up cutting most of it out. But the main point is you have to find a way to express these three terms in terms of the stuff that we have, right? And you can. So after some derivation, you end up with these two integral terms and this simple distribution up the top. These are the three things that were in the Bayes rule before. And suffice it to say, all we have to do is just figure out how to solve those integrals, right? So KF, the original Kalman filter, if you have a linear dynamical model and a linear observational model, you assume everything's Gaussian, and instead of trying to figure out a whole distribution, you're just trying to figure out the first and second moments, then things just collapse and solve nicely. An extended Kalman filter, basically the exact same thing. It's just that you're going to linearize all of the nonlinearity in your model. So you look at the tangent model instead. Uncentered Kalman filter, you perform a spherical integration, which basically means that you pick a few points that represent your density in the Gaussian and use that to integrate. And then particle filter is Monte Carlo everything, and over-converges. So why exactly does assuming that top line, why does assuming linearity, assuming Gaussianity actually help you? Those integrals just represent marginalization, so the marginal distribution of something. And fortunately, the marginal of a Gaussian is itself a Gaussian. Likewise, if you have a linear transformation and you apply it to a Gaussian, you get another Gaussian. So what ends up happening is if you express things in terms of their first and second moments, a lot of things just fall out into matrix algebra, and you get analytical equations that describe the evolution for those first and second moments. Okay, so let's implement an extended Kalman filter on this pendulum problem. So the observations might be a little difficult to see, but we start at time 0, we've got a heavy amount of uncertainty, and we kind of shrink to a little bit, pendulum crosses the 0 line, and then it kind of just shifts up. And it seems to track, it's very certain about it, crosses some observations, hits another point and it shifts up again, okay? You have this large gap where there are no observations, and then over here, it's a regime we've got quite a few observations, so things seem to be rather confident. But, you might look at this and wonder if it's struggling to decide what it wants to choose. And someone who's worked with a lot of Bayesian filtering algorithms will say, no, it's working perfectly fine, because we are using all the information we've seen up until a given point in time. And it's good enough for Apollo. Why can't it be good enough for this random guy in his lab, right? The problem, right? Information is being carried in the same direction as the filter is moving. So if you are only working with the observations you've seen in the past, you're neglecting all the information that's happening in the future, right? So is there not the possibility perhaps where once you've gone forward through the whole time series, you perhaps move backwards? And the answer is yes, you can do that. It's called smoothing, if you ever heard of it. So Bayesian smoothing algorithms, backwards algorithms, they try and estimate this hidden state given all observations made after the hidden state in time, and also the filtering distribution that you computed. So Bayesian smoothing algorithms are actually more broad than this. This is a specific class of forward-backward algorithms, they're called, fixed interval as well, where basically they imply that you've calculated a forward filtering distribution before you go backwards. But a few big names, the Rachtung-Striebel smoother, RTSS, is also known as the Kalman smoother. It's the classic kind of smoother that people tend to. You've got the extended version, an ensemble version, an uncentered version, as before. A lot of history here as well, but less so. It's less popular than filters. Okay, a lot of equations. So I just put these up here to demonstrate kind of what is exactly happening. You know, I said there's a closed analytical form, things just become matrix algebra. I'm going to talk a bit about computation, so it's useful to have just a picture of the matrices that are sort of going on, right? The extended Kalman filter just involves two big kind of phases. The first is the predict phase, where basically you use the dynamical model to try and guess at where the hidden state mean and covariance are. And that's why you're not using any information from observations. You're propagating the covariance via a tangent model of the dynamics, because the J's just represent Jacobians. You've got some additional diffusion noise going on. Then the update phase, you know, you've got an innovation coming from the distance between your observation and what your model reckons is going on. You've got the covariance coming out of the measurement model, a Kalman gain, which basically represents the information gain, having seen the observation. And you use that calculated Kalman gain to update the mean and the covariance to where they should be, given the observations. And for the most part, if you don't make an observation, you do this step. You don't worry about the calculation of this. So you go through the whole time series and you do that. Extended Raphtongs-Triebel, what do? You basically calculate a similar kind of gain, but this one is going to be based off of the covariance you calculated right here. And it basically, suffice to say, it's sort of like conditioning on the forward estimate of the state. So if you run a filter through your whole time series, you make a bunch of estimates of the mean and the covariance, the smoother basically moves backwards and then conditions not forward on observations, but forwards on the filter made posterior. Yeah. That's what it looks like. So you run this on the pendulum model and you get something that looks quite nice. You don't have this weird kind of stuttering effect because you can now propagate information backwards. The trajectory has changed in a lot of cases, and drum roll for the answer. So up the top is the state of the pendulum's angle, and down the bottom is the state of the pendulum's acceleration. So in orange is the true trajectory, green is the smoother, blue is the filter. Yeah. And you can see like there are a lot of points where the filter is quite deficient and quite far from what the answer should be, something like this. You can also see parts where the filter's credible intervals, so the amount of uncertainty it believed there was in its estimate was just way off, so the true trajectory falls outside it. But the smoother is quite a bit more capable. And it's also much more capable at guessing this. I was expecting it to be much worse for this, but it's actually quite good at guessing second derivative. Okay, so that's a toy example. What if instead of looking at the trajectory of a pendulum, that PDE or that ODE just involves, you know, two state variables? We've got something with a much larger state space. So in my case that we're going to talk about later, the state dimension's just about 1,000. Not completely insane, but will involve some computational problems if you try and do it the traditional way. So the three that come up: memory, stability, and speed. Often if you're trying to keep a lot of the matrices involved in memory, you can kill a very small machine. I can kill my laptop easily on these problems. Stability, not much of a problem for the versions of the algorithms that we run, but it can be the case if you run the elementary textbook versions. You can end up with some condition numbers of matrices blowing up. And then speed. You know, there's got to be fast ways of doing this. You know, hopefully we can try and abuse those. And that leads to kind of this field of research. I'm just calling it approximate filtering and smoothing. I think it's probably hard to kind of define an exact term for it, but approximate filtering and smoothing are basically a variety of terms that, there are a variety of methods that kind of encompass how we can perform Bayesian filtering and smoothing algorithms, but by making small trade-offs, improve their performance dramatically. So, you know, first kinds of, these ones, this top one doesn't really have a trade-off. It's just a different kind of filter, but you're changing the trade-offs of the algorithm in a certain way to get some kind of benefit. So working in the information, so with the precision instead of the covariance. Square root filters, where basically you have some kind of Cholesky, some kind of square root decomposition you're doing, and you're working with the L instead of the P. And then low rank and directional methods. So low rank's the one that I'm talking about today, and directional methods are kind of similar to that, but directional methods, basically, you're asking the question of, I know that in my covariance, which is usually the hardest part to calculate, only some directions are really relevant. If I know a bit about the dynamics, I know where unstable manifolds are, I'm more interested in those directions than I am where I know the dynamics isn't that interesting. And figuring out those directions is directional methods. Okay, so StatFem, just going to fly through it. Relevant history. So Gaussian processes and their computational use have been widespread for a while now. Likewise with low-rank GPs, I'll talk about that in a second as well. 2002, Kennedy and O'Hagan published this Bayesian model calibration paper where they say, you don't know the computer model, or you don't know the correct forward model, or you do, but it takes a lot of computation to run it a few times, interpolate with the Gaussian process, you do it in a kind of Bayesian inference way, and you can figure out things like how wrong your particular computer calibrated model is, and all kinds of other hyperparameters of the GP that you use. Stochastic, at the same time, separately, stochastic finite element methods. People have been very interested in solving hard computational problems via finite element methods, but also by injecting a little bit of noise and seeing how that how it works. Statistical finite element methods. So in 2019, Mark Girolami publishes this thing. It's about kind of integrating stochastic finite element methods with the calibration of Gaussian processes. So it's kind of like assuming that a finite element model is wrong somehow, could be that the mesh is bad, could be that the dynamics are wrong, and seeing if you can calibrate a Gaussian process to kind of capture that error. And then further on, nonlinear StatFem by Duffin, and then also in 2022, a low-rank extended Kalman filter, so the forward pass, right? Connor did that. And then the thing that I'm trying to sort of look at is a low-rank extended smoother. Okay, so what are we going to do? Find a model with a reasonable dimensionality. Like I said, I'm just going to go with 1,000. It's going to give me a covariance with over 1 million entries. Run the low-rank extended Kalman filter, design a low-rank extended RTS smoother, run that, and then just have a look at what it's doing. So a model, I pick a model that's chaotic. I pick a model that I know has some pretty disgusting behavior. Kuramoto Sivashinsky. It's this 4th order PDE, and this is kind of the true system that I'm going to work with. So this is the data generating process. Looks a bit like that, the one on the left. It's used in some fluid problems, the derivative form we're using especially. It's been used to model laminar fire, like wave fronts as they propagate. A bunch of other uses as well, but the fluid ones are the ones that we're kind of interested in. And we take some observations. So this isn't the observations we're going to work with, but it's just an example. We take observations well into when things get interesting. So, there's this kind of transient period. This isn't necessarily transient, but let's just say it is, and look at this period where things are really disgusting. Predictive model. So this looks the exact same to the untrained eye. A few differences though. So firstly, we're misspecified. The main generator of instability inside the KS in derivative form model is this parameter. I've put in bold 1.0. In the DGP, it was 0.95. That small difference means a lot. That positive second derivative is going to be responsible for propagating out these really high power kind of instabilities in the model. We've also got, instead of equaling 0, equaling xi, that's a Gaussian process that I'm going to throw into the model. I'm not going to describe too much how it's being propagated into the filter and whatnot. Suffice to say, there's a GP in there. We also are initializing with a misspecified initial condition. So instead of starting with the same initial condition as the true system, I'm just going to chuck a cubic spline on my observations and start with that, because that's probably the best I got. We're going to run it in an LR EXKF. So low rank smoothing and low rank filtering for StatFim starts with examining the square root part of things. So when you throw that Gaussian process into the model, StatFim, the time integration we use generally involves a propagator that is implicit. So a propagator is just a nice way of tying together the dynamics of the PDE inside our discretization scheme. And we have to filter the Gaussian process we're using as additive noise through that propagator. And we do it via a first order Taylor expansion. So if you do that, the kernel matrix of the Gaussian process K is just uppercase K. You can see it kind of gets convolved with this the capital M, which is just a finite element mass matrix. Don't worry about it. And then the Jacobians of the system. And you've got both forward and backward in time because it's an implicit model. But the point of this is to say that this L that represents the low rank covariance comes out to be this quantity, which is 3 square matrices and this K to the half, which is going to be the low rank representation of the kernel matrix of the GP. So the square root representation of the covariance of a GP. How do we construct that? A kernel matrix, if you know GPs, is defined by a kernel function. And I'm just going to use the Matern kernel here. So this is what it looks like. I think all the notation is right. Yes, a bit weird because we've got it in terms of R, but this is what the function looks like. And we want to find a matrix K that is a sort of square root form. And we want that square root form to not just be, a full rank square root form, but to be a rank K approximation. So if you imagine the full P is 1024 by 1024, my low rank approximation is going to be 1024 by some width that is K hat. If it was squared, then it'd be the full rank, but we want to approximate, we want to cut off, truncate directions that aren't contributing much to variance. And yeah, fortunately finding these, very active area of research for GPs, doing them quickly. Whole bunch of methods. So you're given a kernel function, a rank K, how do you generate K optimally, or uppercase K optimally? A couple general methods, so these just work on any matrix. Eigenvalue truncation, so you essentially just do a full eigendecomposition of the matrix, and you say, well, I'm only interested in the top K modes, and you just do it by hand. It's pretty slow because you actually have to do the eigendecomposition. The Nystrom and pivoted Cholesky just involve partial pivoting, or the pivoted Cholesky, partial Cholesky pivots. There's some accuracy problems likewise with Nystrom, which is you are sampling your kernel function at some subset of the points in your domain. Randomized SVD is quite efficient and pretty good, actually. It just involves, it's a bit like red vectors. It's like you take your covariance matrix, multiply it by some random vector, and hope to figure out what the directions of orthogonality, the primary directions of orthogonality in that system are. I don't actually know all the details for that one, but it's very good, and it comes as a black box function. I'm going to use it later. And then there's also GP-specific methods. And I'm not using the GP-specific methods for this specific task, but I will probably use them in future because they are very good at calculating it quickly if you are estimating parameters. So in the future, when I estimate hyperparameters in the GP, it might be important to use these. Inducing points, sure, that's just a fancy way of doing the Nystrom method. More than anything, though, are spectral methods. So these kernel functions turn out to be the solution to stochastic differential equations that have particular spectral properties that allow you to truncate them very efficiently, and you can basically end up with very quick ways of approximating large GPs. It's usually what people in the machine learning space are using. Yeah, and there's a few of them. Ones that I'm using, I just use these two because they're easy and they're fast. I'm not going to elaborate on it. Okay, so what's the algorithm look like? So you want to invert the low rank form of the covariance, do it efficiently, do an SVD. You calculate this kind of gain, which is Bn, update the mean, do a decomposition into a Cholesky, and update it. It's pretty simple. It's not too crazy. There's a bit more going on when you actually implement it. For example, you can optimize the order of multiplication such that you're always working with the smallest matrices possible and you don't form big, sparse square forms. But just as it is, not too bad. Some additional details. I'm not estimating parameters. It's what my previous work was doing, and I'll probably do it in my next work, but not for this one. Handle boundary conditions by augmenting the system. So I'm forming like a overdetermined system and then doing my inversions via the normal equations. And yeah, abusing additional computational stuff like sparsity. More details. When someone inevitably asks a question, we'll go back to this slide. An important one though, how do you choose the truncation? How do you choose the effective value to pick for your low rank approximation? Fortunately, it's not too bad. What you can do is just find out in your circumstance the amount of variance explained by a given cutoff value. And it usually just relates to the decay of the spectra of the given function you're using, or the given kernel function. The squared exponential kernel is infinitely differentiable unless the eigenvalues fall off very, very quickly. So you only need 36, a rank of 36 to explain 95% of the variance. Matern, I think, is third order differentiable in the form that we've used it. So you need 49 members to explain 95% of the variance. But those are still a lot better than the full thing. So the full covariance, 1024 by 1024 over a million. And with our low rank approximation, your L is only going to have 65,500 members. Speeds things up quite a lot. So initial condition. Just wanted to explain how I'm getting it. I set a cubic spline and kind of flew over it. You can fit a periodic, we have a periodic boundary condition. You can fit a cubic spline with enforced periodicity to the observations, and you'll get something like this. So my initial condition is the thing in green. My observations are these little blue cross marks. One of the reasons a cubic spline is great is I can easily get the second derivative, which is when you solve the PDE, you have this biharmonic fourth order term that requires you to double the state dimension to handle it. That's what I do. So using the second derivative of the initial condition is nice. And you can see we get something that's relatively good. We've got 52 observations in space, which means we fit it quite nicely. But we're missing some of the peaks. There are some places where we miss, some places where we introduce other peaks. See how they get propagated through. Some results. So up the top left is the relevant part of the data generating process. Top right, observations. Middle left is the filtered, the sequence of filtered distribution means. Middle right, the sequence of smoothing distribution means. Bottom left, pointwise covariance from the filter, and bottom right, pointwise covariance from the smoother. So it's a little tricky to see. Kind of wish the plots came out a little better on the screen, but there's a couple interesting artifacts. Like, for the most part, these perform quite well. They're actually matching very well. There's a couple problems though, like you can see on the boundaries, we have some problems. Some of the modes don't carry, they kind of just end. The smoother tends to do a little better as it introduces stuff from the right-hand side, but the filter kind of just ends. Other modes just sort of suddenly appear in the filter as it makes an observation of it just appearing, whereas you don't really see it evolving in. There's also, if you can see, just a bit of graininess to the filter, and that's the result of the fact that you are conditioning on those observations. You're seeing that downshift we saw in the pendulum, right? As you constantly shift to those observations. And the smoother is able to propagate information backwards and able to handle that. So I'm going to start flying through these because there's something else I want to talk about. The states all look quite good. Sure, you know, top plots, RMSE, hey look, the smooth is better. Who would have thought? The negative log likelihood kind of punishes a little bit, but it's not too bad. And that's it, right? Lower error, better. I kind of got to this part of the manuscript and I was like, I kind of need to do something else. You know, I kind of need to contribute something here. What else can we discern? So I had this idea, you know, the means look different, as you'd expect. The credible intervals, just when you sort of look at them like this, they just look smaller. You'd also kind of expect that. But is there a way of trying to examine that a bit closer? Like pull that structure out, see a bit more from it. I'm going to go on a bit of a tangent. So eigendecomposition, every square matrix is describable via eigenvalues and vectors. You know, you do this kind of decomposition, unitize eigenvectors. The eigenvalue represents the amount of variance associated with the direction given to the eigenvector. That's just PCA if you've ever done it. Idea number one. Is the primary direction of uncertainty in the smoother completely different from anything the filter has predicted? So you do this decomposition for the filter and for the smoother, and you ask the question of whether the first eigenvector from the smoother is ever not in the subspace spanned by the eigenvectors from the filter. If you wanted to test that, there's a score. You basically just look at the squared norm projection of that smoother eigenvector in the filter subspace. And you know, if that equals 0, then it's entirely within that subspace. If it's 1, you've got orthogonality. What a great idea. So you run that over your time series, over the sequence of filtering and smoothing distributions. Never goes very high, which you might expect given the fact that the smoother is recursively defined based off the filtering algorithms. There's never new directions it can kind of explore because it's not utilizing any new information. So a second idea. Maybe it's never going to give us something completely new, but maybe it can give us something unexpected. Is the primary direction of uncertainty in the smoother ever novel given the filter? So that's a question you can ask. How do you measure novelty? So there's many different ways. It's more of an information theoretic question. You know, you look at surprise and things like entropy. Statistical distances, things like KL divergence. Here's a simple idea. Let's compare the amount of variance the smoother gives to its main direction to how much the filter gives its directions. So I say think finite portfolios because I'm thinking of, you know, you look at two investors, one saying I allocate 80% of my wealth to stocks, and the other says I allocate 40% of my wealth to stocks. And then this one says, you know, 10% to gold and 5% to gold. Those allocations are the things that we're interested in. So the amount of variance the smoother gives, the amount that the filter gives. Now, you want to look at proportions. So the thing is, the smoother is always going to be more certain than the filter. And I kind of want to get rid of that. I just want to look at proportions. So what I do is I take the weighted or normalized eigenvalues and I want to compare those. So proportional weightings of variance given to each of the respective modes in the smoother and the filter. And here's a score. Because they can scale really small and really large, I'll just chuck a log on it, right? So the sum of this quantity. Is that a score that works? You might realize very quickly there's a bit of a problem with it in the sense that the weightings are incomparable because they go in different directions. So the smoothest primary mode is allocating a proportion of variance in the ith eigenvector in the smoothest direction, right? You need to find a way to reshuffle it so that the directions match up. And a solution. We were looking at the alignment before. Let's bring it back in. So you now have this score that involves both of them. And you want to see how that looks over the time series. Plot it. Get something like this. So high scores represent novelty, I'm hoping, and low scores represent whatever the opposite of novelty is. Boredom, maybe. I don't know. I put some thresholds because I want to figure out what these things actually represent and just pick out the most interesting scores and see what they represent. And down the bottom here, the notation's a bit rough because of the manuscript, but this is just the total uncertainty in the filter. I just put it here as a validation statistic. Here's a positive event. I'm going to call it a promotion. So up the top are the scaled eigenvectors from the filter. I've got 20 seconds left. They're the scaled vectors from the filter, eigenvectors based off of that proportion. You can see all of the modes of the filter represented, and then the very first scaled smoother mode. And my question is this first smoother mode in a direction or completely different to anything the filter predicted? And you can look at this and see, well, it kind of is. There's a bit of, the filter's sending a bit of variance here and a bit of variance here, but the smooth is kind of a little bit outside of that. And the way that this score is calculated is shown in these two plots. So the first one is the alignment between the first smoother mode and all of the filter modes. And the second one is this log importance ratio. So it's the weighting from the smoother against all of the modes from the filter. And all you do to find the score is you get this number and you just multiply it by the corresponding column here. And then you add across the whole thing. So this score, you know, I think it's the 11th and 12th modes of the filter that the smoother primary mode is aligned with. And basically you just take these quantities, multiply them, and then add them. And that's how you get a score. So that's what a promotion event looks like. And it looks pretty good. It's kind of like the smooth is saying, you know, you need to really focus and allocate more variance to the very edges. Here's a demotion, the opposite. So the smoother is very confident that the filter's primary sort of direction isn't as important as it needs to be. It doesn't need to send as much variance in that direction. And these aren't that interesting, but it's always good when you calculate a score like this to know what positive and negative readouts really mean. I've got a couple other cases. It turns out that every single positive score in this sends uncertainty to the boundaries, which revealed to me a bug in my code, that when I was calculating observations, I made them equidistant across my domain. But because I have a periodic boundary condition, you end up with a little bit of extra on each of the edges. And so the smoother was basically telling the filter that you need to focus on this extra bit of distance between your measurements, and the filter wasn't picking it up. So the smoother basically sent uncertainty there every time. There's another one. All of the demotion events, interestingly, were focused on these three primary kind of peaks in the state right here. So the filter always had a certain amount of uncertainty associated with them. And whenever the smoother sort of corrected it, swung past it, it always said to just be a bit more confident about it. Yeah. So quick summary, smoothing's useful, it's worth doing. Low-rank approximations ended up being very effective and very fast. So I compute these in about an hour. I do a full simulation across, you know, 1 million whatever. Sometimes the filter gets its allocations of uncertainty right, but not the right places, and the smoother seems to be fixing that. Thank you very much.
Yeah, thank you, Daniel. Are there any questions from the audience?
Go back 2 slides. So this sort of thing. So you're doing this, you're taking a slice through your Kuramoto.
You mean like in time?
Yes, this is for a single time.
Yeah, this is t equals 195.6.
Okay. And so you're doing this for all time?
I calculate that diagnostic statistic for all events, for all time, yeah.
And you get another time series out of that?
I get this one, the top.
Okay, that's what this is. Okay.
So this is the score over time. And basically every time an observation is made, because the filter is so certain after that observation's been made, because information carries forward for the filter, you can see after an observation is made, there's not much gain that the smoother's making, but it's right before an observation where the filter's most wrong that the smoother's making the biggest novel kind of corrections to the structure of the uncertainty. If that makes sense.
Can you say all of that again, but with the Kuramoto state?
This one?
Yeah.
So you run the predictive model forward in a filter. I make an observation. Because I've made an observation, I now know what my model should look like. So I decrease the uncertainty and I shift the state of my, predictive filter mean to wherever that observation was. And I keep doing that all the way through. The problem with it is that if you are shifting, like you move forward and I say I have to move completely, it says nothing about what was happening behind me because of the whole Markov process, right? All the information is being carried forward. So the smoother basically says, okay, now let's do it backwards. We start at the very end and we start moving backwards, and I know that these corrections are happening. I can then fix the little guy right behind it. And it's fixing the mean, sure. It's lowering the uncertainty, it's decreasing the variance, sure. But those plots, I'm trying to discern a particular sort of characteristic of those corrections, which is how is it reshuffling the directions and proportions of that uncertainty? I know it's decreasing them, sure. But if the smoother says you need to allocate all your uncertainty to this direction right now, and the filter said that there was no uncertainty in that direction before, that's a novel event to me. That's what this score picks up, or I hope it picks up, based off the logic. It's an empirical statistic. It's not the log of the weights, some might say, is a kind of KL divergence, but it's a thing I'm still arguing with Ed about. So, yeah, I hope that makes sense.
I may have totally misunderstood what you just said to chat just now, but in that case, the novel events, as you're scanning backwards, right? If you go towards observation, the smoother is telling you to hey, there is some uncertainty. Put more focus on this part. Does that mean that the novelty of the event is related, or it's mediated to some extent by the uncertainty in the observation itself?
Absolutely. Absolutely.
So then, if I were to bump up the uncertainty in my observation, because at the start of the talk, you assumed a very, very small uncertainty, right?
For the pendulum. For this one, my uncertainty, all I worked off for the scale of the measurement noise for this case is I'm doing 4 times the measurement noise the last person when I read the paper that used this model is using. So it's a decent amount of measurement noise.
All right.
Yeah.
So, but essentially, wherever you see novelty, it's basically saying, filter, you're being too confident that it's the correct measurement. There is actually possibly more uncertainty here than you think.
Yeah, I say novelty. What is it? It's not. I'm not saying surprise. I'm not appealing to entropy or anything. But it's just basically figuring out structurally, in terms of an eigendecomposition of the smoother covariance, how the filter and the smoother differ at a particular point in time. And that, the difference is usually largest when you make an observation, because the smoother is saying, I can see that this is going to happen. You need to correct. The filter needs to correct, because the filter only carries forward. Smoother is able to do it backwards. And that difference is usually just a shrinkage. It's usually just a shrinkage. But I want to characterize sort of what that shrinkage really looks like, which is why I work in weighted eigenvalues and I focus in on the directional uncertainty. And that's all that this thing is. It's literally just an empirical statistic I use to try and glean out these events. Because, I'm not going to make an appeal that there's a probability distribution underneath and all those kinds of things. It's just empirical. Maybe that's a weak thing to say. I don't know. Yeah.
other questions? That is not the case, and let's thank Daniel again. Next week we are going to have Marcus.
Maybe.
Talking about something else I don't know anything about.